Hey everyone, and welcome to our ECE 484 final project, GAN I Detect Lanes. The motivation behind this project was that we realized that the MP1 lane detector implementation fails in different weather and lighting conditions. So instead of changing the pre-existing hardware, we decided to act on the image that was being received by the lane detector. Our claim was that modification of a non-day image to a day image should yield lane detection as good as day conditions. Or, in other words, we should be able to convert a night, snow, or rain image to a day image to improve the lane detection compared to the night, snow, or rain conditions. Here's what our final architecture ended up looking like. Basically, we had the input of a night, snow, or rain, and then we converted it using a cycle GAN. We had 3 separate cycle GANs for each of these conditions. Then, once we have the converted day image, we were able to perform lane detection on the hardware of the car.
So let's begin and talk about generative adversarial networks, or GANs for short. GANs use 2 neural networks, a discriminator and a generator. The discriminator tries to distinguish between fake and real images, while the generator tries to create fake images. The goal of the generator is to fool the discriminator. So if you train this enough, eventually you'll get a discriminator that can't tell the difference between fake and real images. One thing to note is GANs can take a long time to train. For example, this image is generated from StyleGAN2, but StyleGAN2's training time took about 7 to 9 days with 8 GPUs. The other thing to note is that GANs don't really have a well-defined metric. One of the only metrics used in papers and literature is FID, and we also use visual check. So we really have to be careful when we're defining metrics for our GAN here. So we use a specific GAN called CycleGAN. And what CycleGAN does, it takes 2 unpaired data sets and tries to map them to each other. So for example, let's suppose we have this horse and zebra data set. First, we'll convert the horse to zebras using one GAN, and then we'll convert that zebra into a horse, and then compare the generated horse with the actual horse. And we call this loss called cycle consistency loss. And so essentially we're trying to map these 2 data sets, and it's very useful for image to image translation. So if we want to translate a snow to day, we'll first convert our snow image to day and then our day image to snow, and then compare the 2 snow images generated so we can calculate our loss. So one thing to note about GANs and CycleGAN in particular is we need a lot of data. So to do this, we ran our gazebo environment with modified textures to emulate rain, night, and snow. And so what we needed was day and non-day images for the CycleGAN. And so at the end, we looked at the paper for CycleGAN and we realized we needed about 1,500 images per each setting. And so that works for the simulation. And we did the similar thing for Carla as well. And now for our real life data, what we did is take it from this once data set, which had about 80K night images and 120K day images. And for our snow, we use BDD 100K, and that was enough data to actually train our GANs.
So as a proof of concept, we decided to first implement various map environments in Gazebo. This was to not only do a sanity check on our claim, but also to make sure that our CycleGAN could successfully handle very trivial scenarios. So here we have a night scenario and a snow drive scenario that we made in Gazebo. And once we input it through our CycleGAN, we can see that the converted day images for both the night and snow images look very visually similar to the ground truth, indicating that the CycleGAN can handle these very trivial examples and kind of giving us the green flag to move on with more complicated examples. So regarding complicated examples, we decided to use Carla. And the reason is, well, there are multiple. Carla is much more realistic than Gazebo, and it's also very easy to have unique weather conditions and also very different location and tracks. So you can see a rainy kind of a countryside drive over here on the top, and then a more nighttime city-ish drive on the bottom. It was also pretty easy to integrate an open source lane detector algorithm we used, although we had to modify it significantly for our needs. And it was also very user friendly to collect data, although the setup took a lot of time for us.
All right, so for our metrics and results, one thing we did for the lane detector was just doing visual confirmation, which was just looking at it and seeing was it actually detecting the right lanes. However, when we were testing our GAN and trying to evaluate it, we found two metrics. One was just the basic pixel by pixel comparison, but we also found something called an FID score, which is specifically related to GAN success. And we found that that was a lot better. And I'll explain why in a little bit. The FID is actually short for Frechet inception distance, which is a pretty common metric for GANs. And the basic idea is it uses a convolutional neural network called Inception version 3, and will basically extract features and generate a multivariate Gaussian distribution based off of the output of that. And then we take the Frechet distance between them, which is a common math term, which just has a formula below. Turns out this does a really good job of mimicking human perception of similarity, whereas pixelized comparison does not always have that advantage. And then here are our results. We thought these ended up being pretty good for our GAN because most of the papers we've read have had an FID of around or a little bit less than 100, and this is right around where our results were.
So here you can see our lane detector working at night, and it doesn't do a really good job of finding the lane in our night image. But if we actually take that image, convert it to a day image, you can see this is what the following path would look like. And it does a pretty good job of finding the lane on straight paths. It does have some issues when we go around these corners here. The image becomes a little sketchy when we go around these corners. We believe because of the upscaling needed from these smaller images in our GAN. So that would be something we would fix if we continue with this project. But for the most part, when we're going on straight paths, it does a pretty good job at finding the lane. So when we move on to our rain, you can see in the rain just does not find it very well. The lane detector really doesn't even work at all. And in fact, this clip is short because it crashes. But if we move on to our actual rain converted image today, it does have some issues finding the lane as well as the night, but for the most part, it always is getting one side of the lane. Even in this speed change here, it keeps consistent with finding the lane. So we would call this a success for our results for our first GAN that we trained, and then go from there and keep improving our GAN to fix some of these scaling issues and things like that.
So I learned a lot in ECE484, and I think my favorite aspect was definitely the particle filtering because of the probabilistic approaches that were used during that unit. And I think the project gave me a lot of time to understand lane detection as well, since initially I was not as confident on that, but since I've spent some more time, I think I'm also starting to like lane detection.
So personally, for me, 484 was a really fun class. My favorite part of the entire class was probably MP1 with the lane detection and perception. Personally, I come from a computer vision background, so seeing some of that computer vision knowledge being used in an autonomous car was really cool. And it really demonstrates how complicated an autonomous car can be because you have perception going on, you have control going on, and you have so many elements just going on all at once. So this, the first MP really inspired us to do this project and really push forward with what we can do with computer vision and how it can be used in autonomous vehicles.
I overall had a very positive experience with ECE484. I think it opened my eyes a lot in regards to the nuance and complexity that goes into implementing safe autonomy. And the most exciting part of the class for me was definitely the lane detection project because it also introduced me a lot to the amount of nuance and tuning lane detection requires. Additionally, it also kind of provided motivation for this project because we realized if it's so complicated to tune a lane detector in this one simulator scenario, we want to be able to make sure that all conditions can hopefully rely on the same lane detection algorithm rather than tuning a lane detector for all these different conditions. We thought it would be much easier to just convert extraneous conditions to a standardized condition.
Throughout my time in ECE484, I really enjoyed learning about the perception and planning based algorithms as I really enjoy the theoretical and mathematical discussion behind practical problems. I felt this course did a really good job at bridging the gap between practical problems and the theory behind them, as I feel like that's a huge problem in the real world. This really helped in the project because it allowed me to adopt a mindset that brought out practical issues very early on so that we could adjust the scope of our project before realizing that later on that there were problems when it was a lot more difficult to change things.
My favorite part of EC 484 was the controls part. I really thought it was interesting to learn about the bicycle model and the different controllers and things like that. So, and then for our final project, I think the biggest thing was like MP1 lane detection, learning how to do that, kind of getting that mindset down, so how we could apply it to our project. So